This looks great until you start thinking. So suppose that I take a random point, x0, from my world, and I run the simulation, I get some number. Then I get sneaky and I make this point to be equilibrium point. Well, I get a different number, because if I'm in a state space and observable is non-trivial, so it takes differing values over the state space. So I can draw it this way. I can say observable is something. Here is my state space, and this is the value of the observable, defined as a function of the state space. If I only measure it here, I'll get one value. And this value might be totally unrepresentative of the system. I may measure it where the thing is frozen, but it's hot every place else. So this is actually a very tricky quantity, because I know I have, so far I know that I have infinitely many solutions on which each one of them will only probe locally the state space. So in principle, each one of them has a different value. So it's not obvious at all. This is totally wild. So then you think about it, and you can prove theorems, etc. But one thing that you obviously want to do is you can say, what's wrong with this is that I'm averaging over a single orbit, but I know that kind of averaging I can do requires also averaging over space, because I know that I can precisely specify a single orbit. So I should really give initial condition which is spread out of space. And now we'll be saved, because these things exist, but they sort of measure zero compared to normal conditions, because to find one of these solutions I have to specify it infinitely precisely. So they're like rational numbers on a unit interval. They're all there, but if I throw a dart on a unit interval, I'll never hit a rational number. And if I define something only on rational numbers, I won't have enough measure to define the integral, etc. So, but obviously what we have to do is we also have to think of space. I have modern notations. I'm using bar for time and brackets for space. So what I'll now do is I'll take all initial points. Each one of them I'll start a trajectory, and I'll evaluate the time where this xt is the trajectory at time t of having started at x0, but now I integrate over everybody. So that's one space average. Now, if you don't like the space average, it depends on time, so I have to put a time, because it changes time. If you don't like it, you say, well, that's kind of crazy, because why would I prefer something that starts uniformly every place in a state space? I usually prepare a localized thing. Then you can define it with respect to initial distribution RT. So this can be very peaked. If you're really kinky, it can be a Dirac delta function. So that's how you would do space averaging. You would describe what I prepared, and then you would like to know what the average looks time t later for that object. And that sort of looks much healthier than just looking at a single time average. And then you can boldly declare that what I really care about is something I'll call expectation value. What I really care, I'll put the brackets here, but without time. And I say what I really care about is, what if I start every place, and then I compute average, time average, for each point in that space. So time average is, this thing for each point. So I do an average over space and time. So that should be robust, right? I start every place, I integrate everything, I have to get a number. This cannot be very sensitive to anything. This can be the most robust thing I can do. And if you want, again, you can put a little row here, if it makes you happy, for initial distribution. So that seems a good thing to do, because we know that in infinite time we cannot predict where it came from, because we lost all the history of it. So the best I can do is say I came from every place and average over all of these things. So I could define a thing like that. and then, sorry. So this is over space, and then over time, t0 quantity. So this is now average of all trajectories. I take the whole space, and I move it for infinite time, and I divide by all the right numbers, and I get an answer. Again, so now if you're a mathematician, you go home, because now you've done it. But you actually have cockroaches running around your lab, you have to produce a number. So this, you can do on computer, this calculation for some simple systems. So you can actually simulate and do it, and you get a number. But how do you really, really do it?